On the screen are 6 common everyday objects and experiences. Our challenge to you is to identify which of these things are caused by plant chemicals. You should be seeing a prompt shortly to input your choices. You'll have 1 minute and 30 seconds to place your answers. All right, time's up. Let's see what everyone chose. It looks like the 2 least popular choices were rubber bands and cardinal feathers. But don't feel bad if you chose those because everyone's a winner. On your screen, you can see that all of these phenomena are actually caused by plant chemicals. We'll go over the explanations to the 2 least popular choices. Cardinals actually get their red pigments from the seeds and fruits that they eat in nature. They then build these pigments in their feathers. For rubber bands, they're actually when they're made of natural rubber, they're actually made from the plant chemical isoprene. Right, now that the idea of plant chemicals is cozy in everyone's mind, I'd like to introduce to you today's speaker, Dr. Sibongile Mafu. Good evening, Dr. Mafu.
Good evening.
From that game we just played, it's obvious how crucial and commonplace plant chemicals can be in our everyday lives. Why do plants make such potent chemicals, and what do plants use these chemicals for in nature?
Okay. That was a great poll and it was a good introduction. So I'm going to begin sharing my screen so that I just have some visuals. Give me a minute. All right. So plants are considered to be organisms that don't move, right? So when we think of them, we think of them that they're sessile and they don't move. If you talk to plant people, though, they'll not agree with that totally because they think that they're little movements, right? But in general, plants have to adapt to their environment. They have to get their nutrients. They have to be able to um, adapt to the small changes that happen in terms of climate change, in terms of stresses, and then defend themselves. And so for this reason, they have come up with a lot of ways to be able to be in sync with their environment. And one of those, and which I think is the most important, but I'm also very biased, is chemicals, right? And so that's what they use the chemicals for communication. And so this particular picture, it's dense and it's got a lot of information, but it is just showing the many interactions that plants have to use the chemicals to communicate with the environment. And so they need to be able to pollinate. And so they produce volatiles that will tell the pollinators it's time for pollination to take place. And you talked about the color of the cardinal feathers. It's the same thing with the colors of the plant leaves and the flowers. Those are also from chemicals. On a definite level, they have to protect themselves from insects, from microbes, things that are going to come and ingest them and infest them. And so they produce a lot of chemicals that can deter feeding heavy insects and and antimicrobial. So they produce a lot of toxins as well. And we always think about it on top of the ground, where the things that we can see. But plants get quite a lot of nutrients from the soil, and a lot happens underneath there with the roots and everything like that. And so the same chemical interactions that we see happening, or we visualize happening on top of the ground, also happen at the bottom. So they've just produced the chemicals to really be able to survive in whichever environment that they're in.
Wow, it's obvious that plant chemicals are super important to survival in the wild. But it's weird because we use plant chemicals to our own benefit. Are there any other effects that these plant chemicals can have on humans or other animals?
There are various effects. Uh, just using the plant chemicals that we try and avoid. There are quite a lot of things that we try and avoid. So as I said, they produce a lot of toxins to really defend themselves and make sure they're protecting themselves from little microbes and insects and stuff like that. And so those chemicals can also be harmful for humans. But at the same time, and so example here is a couple of plants that we tend to avoid that produce a whole heap of, that produce chemicals that we have adverse effects to. And so poison ivy is an example of that, right? And then there's things like belladonna from the deadly nightshade that in novels and in history have been used from killing people to actually dilating pupils. And in all of these three examples, as much as they're all harmful, okay, in the wild, whether to animals or to people, they're also still uses for them potentially for traditional healing. So people, if you're used in right amounts and in right concentrations, they can still also be used for healing purposes.
Yikes, I'm glad that I don't have these plants growing in my backyard. But don't even these plants need animals to spread their seeds?
Um, all, I gather all plants need a way to be able to survive. And so even though they're producing these toxic chemicals, they may not be involved with their seed dispersal system. So if we look at this Gimpy Gimpy, it's producing its toxic chemical, but it's also in trichomes that are on the leaves. So it can still have its method of seed dispersal unaffected. So one thing about plants, they're also very intelligent, so they know they need to survive. So they've sorted that out, whichever way they've decided to do it.
That's so awesome. Well, how about some positive examples? What are some beneficial plant chemicals for us? And do other animals use it in the same way?
Um, so beneficial examples, I think every time chemicals are all around us. And so we sometimes think about it, or really we don't. So every morning when we have our cup of coffee, that's, those are chemicals that are around us and we never really, I don't think we think that they're chemicals, but they are, right? And so when we're cooking and all the spices that we use, those are great chemicals that that are in constant use. I like to use rosemary as an example because it transcends a lot of aspects that I always think about. And so if you think about rosemary, we take it we like the smell, right? And it's a great cooking spice. The same compound that is giving us this great flavorful scent is also then great as a herbal remedy. So it's actually part of the herbal remedies and people use it for weight loss. It's a very good antioxidant. And so it's also great for skin and cosmetics. And in the plant itself, it's used as a survival compound, and it's a response to stresses like UV and sunlight. Okay, and then it's got these properties that then can prevail transcend a lot of things, from the human aspect, from the animal aspect, for the plant survival, and then for our own culinary tastes. So they've just got these very diverse uses that, depending on which system you're looking at, we're just using them all differently.
Wow, all of this makes me wonder how many different plant chemicals are part of my daily routine. Um, that being said, this wraps up the first vignette. We will now take questions from the audience for the next 5 minutes. Please use the Q&A function at the bottom of your screen to ask questions, and we'll try to address them as quickly as we can. Oh, you may also raise your hand using the raise hand function if you have a question.
As we are thinking about questions,
Okay, we have three different questions here. The first one is, what are some positive ways that the dangerous plants you mentioned earlier can be used?
okay. Let's go back to the screen with the plants. And so when we look at all of these, okay, I'll start off with this Australian stinging plant. So this one causes a lot of pain. So it's really painful, and people have adverse effects to it for quite a while. But at the same time, it is also a chemical that has been shown to be have great anti-cancer activity. It targets one of the cancer targets. Poison ivy, as much as it's harmful, the plant itself can actually, in a traditional scale, has been used to treat pain. It's also great for rheumatoid arthritis, and menstrual cycle swelling. So things to do with inflammation and pain, it tends to treat very well. Deadly nightshade is just an example I like using. I used to read so much about it. Things people in early on, it was used to dilate pupils and stuff like that, and also early on, it was in Roman times, and further on a little bit later, it was used as well as an anesthetic. So they would mix it with opium, and so it was also used as an anesthetic. And as long as you're not using, and local or traditionalists do use it still for lots of remedies, but you just have to use it in the right concentrations. On an FDA level, it is not approved at all.
Thank you. The next question from our audience is, are these chemicals typically expensive or resource intensive for plants to make?
Um, Generally, not really. The plant has to make them. When the plant is making them, it's making them for whatever reason it needs to. We don't always know those reasons because it's very difficult to have experiments that will tell us why a plant is making all these diverse chemicals. But we always assume that they're for defense or some type of mechanism that's going to help it to survive. For that reason, it uses the same chemicals that they draw off from systems in the body, in the plant, that are already being used. So we need carbohydrates and lipids and amino acids. So these chemicals tend to be made from the same pathways, and they just draw off from the same biosynthetic pathways that are used to make those basic chemicals that are required. And if it definitely needs it for survival, becomes essential as well at that particular time. Otherwise it dies and then there's no point anyhow.
And that's definitely some things we'll be talking about later in the second vignette, I'm sure.
Yeah.
There's one final question from the audience. Have there been any experiments done addressing these plant chemicals, at least the ones you've spoken about so far? Like any interesting experiments that like you might think of that you know of?
Um, Most of these, if we look them up, have been tested. And so we would be able to find some experiments. Sorry, I can't come up with specific examples right now.
Okay. Um, that being said, I think that's enough time for questions now. Before we move on to vignette two, it seems, Dr. Mafu, that there are some chemicals that humans like to use that you know very intimately, some terpenoids that you might have studied.
Some terpenes that I might have studied. Um, okay, so I'm going to just go back a little bit. So related to the chemicals that we do use every day, I work on a certain class of chemicals called terpenes. And with time, whether it's terpenes or any other class, we tend to use them for a whole lot of um, society has adopted them in because they've become very useful. So in the class of chemicals I study, they're particularly used as pharmaceuticals. And so Taxol, which is a chemotherapeutic from Pacific U, is a very good example of that. And if you go to Sephora range of products, so if you like shopping and you go to any departmental store. As I said, they're great. Same way as rosemary has antioxidants that are great as cosmetics. These products do tend to have a lot in terms of cosmetics, and so you'd not think about it, but they're actually uh, very good as emollients, and so they're ingredients in like the Biossance range of products, which um, are marketed by Sephora. And so all the fragrances, and so the same way the plants are using the fragrances to communicate with the environment around them. Terpenes are in spring. It's nice to know when I walk around, I am smelling terpenes. And so terpenes are actually very great fragrances. And so Chanel No. 5 is kind of an example of that. And just to highlight again, rubber, which was there in the poll, is something that took me a while to understand that it actually is a terpene. It's just a terpene that's very long and it makes rubber. Okay, so that's the class of compounds that I study.
Awesome. And again, it's just fascinating to see how ubiquitous plant chemicals are in our everyday lives. Um, Now that we're done with vignette one and questions, let's move on to the second vignette. And we'll be talking about how plants make these chemicals. This far, we've talked so much about why plants make chemicals and how we interact with them. Let's talk a little bit more about the process involved in making these chemicals. So how exactly do plants make chemicals? Um,
Do you want to finish off your question?
Oh, and yes, this was interestingly brought up in the first vignette by one of the audience members. Is it hard and expensive for plants to make these chemicals? And are there any trade-offs that they have to make in order to be able to afford these chemicals?
Okay. Yeah. So yes, so it was nice to get that question early on. And so as I said, the plant does need to make the chemicals for a particular reason. And so we'll go first through how they make the chemicals and what that means in terms of um, flux or directionality to the different systems. Um, so these chemicals, as I said, there's a distribution from the essential ones that we use, the same way we need our proteins and our carbohydrates from our meals. The plants need to make that for their daily survival. And so those are really essential or primary metabolites, as we'll talk about them. Um, and whether it's a plant or a human, all of these chemicals are made by small building blocks. And so you could think of it as a Lego game. And so it has to really, you have to put in the small units together and keep on stitching them together. And so so basically it's putting all of these small building blocks together. To do that, the plant or any organism really uses different enzymes. So these are proteins that are then going to come and take these small building blocks or these small little chemical units and start stitching them together. And there are millions of different types of enzymes in any system that then do all of this work. And so this is an example of some of the enzymes that are used in terpene biosynthesis, okay? And so these enzymes will all do different block stitching, basically. So this is an example. So for this first block, it will just, for this first little backbone, it will be created by this particular enzyme over here, the first enzyme. And then after that, you then have another enzyme that's going to close up this ring. So its job is just to, add that structural, make it more sophisticated. And then this one comes in, another enzyme will come in and start adding the different little groups. And so you see these small little changes, that are as you're going from one stage to the next. And so this is all to build one molecule. And in all of these examples that we've shown you, whether it's in rosemary or any of the other things, the pathway can be very long with a lot of enzymes from anything between 5 to 30 or even more. And that's really just variable depending on the complexity. So do you want to go back to one of the other questions? So this is how they make it. You just use building blocks, enzymes, and you get this complex pathway. And that can be very variable.
I see. It's almost like an assembly line is inside every plant.
Yeah,
Um,
it is an assembly line.
well, every assembly line needs starting materials to make their final product. Do plants need any special ingredients to make these chemicals? Anything that they take from their environment, for example?
So as I said before, it's just the same things. And so just carbon, hydrogen, and oxygen. And so that's all the most of the basic chemicals will just have variations of carbon, hydrogen, and oxygen, right? And then the others will then have some plants, some chemical classes will then add nitrogen, sulfur, and a few of the other chemicals. But the most basic things that you're always going to find is just carbon, hydrogen, and oxygen. And it just gets that from the same biosynthetic pathway that you're getting your carbohydrate, lipids, and proteins that you use for your diet.
Interesting. So if all chemicals are made from the same basic ingredients, um, there's a diversity of chemicals in the plant world. Does that mean that all plants can make can make all these different chemicals using the same ingredients?
They can make the similar types of chemicals, but this is where it becomes, um, it, it's really an adaptation to whatever environment it's adjusting to. And so there are some classes of chemicals that may be found in all organisms, okay? And so, the ones for pollination, so the small terpenes, you'll tend to find variations of the same thing in all organisms. And then there's some which have evolved specifically in that range of plant species because it needs to adapt to a certain environment. And so those are the things that make plant metabolism like awesome to study. There's this variety that you can't pinpoint. And you only get to know it by actually looking into it and saying, oh, okay, so this is produced for that. Yeah, and so there's just this great variety that you can't actually pinpoint. You can say this class can be found in here, but there's always going to be something that's just going to pop out and be new. It's got this wonderful way of being able to adapt and really produce new chemicals as is needed, depending on the situation it needs to do so.
Wow, it looks like there's just I agree, there's such a diversity of plant chemicals, and it's so interesting to study all of them. Obviously, one person can't study all plant chemicals. So what plants in particular have you studied, and what do you study now?
Okay, so, all right, so I'm going to take you're going to see a little bit more of enzymes and chemicals again. But so when we think of chemicals, most of the time we think of all of these medicinal plants and the really exotic chemicals. But I want to really always reiterate that these are found in all organisms. And so my previous work, really, I'm a biochemist by training. And so I actually focus in on the enzymes. And from grad school, I've really looked at enzyme diversity and more enzyme evolution. So how this great diversity that I'm excited about has really come about, and looked at elucidating those particular pathways. So I've done this really on an evolutionary scale where it's, so plants, as we said, they started off like 400 million years or so ago. What we know is that plants came onto land, right? And then they had to start adapting to the land. And so they had to start making this different chemistry. So I look at how the plant's chemistry has changed as the plants have adapted onto land. And to do this, then we use these little different plants from different lineages. And so there are these little things called bryophytes, and this is an example. So this Macancia is an example of that. And so they're the earliest things. So they're just little, they don't really grow very big. And so you really find them. So it's like your moss, right? Then you've got your ferns, the lycophytes, and that is resembled by this particular system, Selaginella. And then you get to these higher plants, things that we tend to see around us now. And so these are systems that then would resemble that. And so I would look at enzymes in all of these plants, and that would tell you how a certain terpenes have changed over time, or how they have become more or less, or how the enzymes have changed. And so I tend to look at how these enzymes have changed to really look at that metabolic diversity. And I've also then taken those skills and then gone to look more at pathway elucidation in some crop species. So rice is also a crop, but I've really looked more at how compounds are made in maize. And what we've found is that maize makes a lot of terpenes, and it uses them to defend itself against fungal organisms. And so we look at how those enzymes are there in that particular plant, and how they have and how they respond to fungal infection in a way. And with time, I've also looked at some of these medicinal plants. And so for me, it's more the enzymes that make them and then make that particular diversity. And I just want to really highlight this, that all plants have got this wonderful diversity. And so it's not always looking for the exotic ones. And so things in our backyards, or things that are crops, which we think might be boring, are actually very chemically diverse as well.
Awesome. You mentioned something about fungal pathogens and how plants defend themselves against them. Are chemicals involved in that as well?
They're involved in two ways, yes. So as I said, the plant can't really move, so right, it has to stay there and it has to defend itself in some way. And so when it is attacked by fungal or bacterial organisms, or just by insects or herbivores, it has to find a way to make sure that it can protect itself from that. And so one of the response systems is then to produce an array of chemicals that are toxic to that particular organism, and hopefully it can kill them off. There are other ways that it can also protect itself, but as I said, I'm biased and I think chemicals are the most awesome. Okay.
And so these are plants that you studied before. What do you study now?
Uh, so it's just really, I've changed to more the same way that the plants produce chemicals, fungal organisms produce chemicals, and they also want to adapt to their environment, right? And so their environment sometimes are plants, right? And so they produce a slew of chemicals so that they can either infect the plants or live in great harmony with it. But at the end of the day, I now look at fungal organisms and the chemicals that they produce and why they produce them. And so this is just the same way plants have got a great chemical diversity, fungal organisms have got an immense chemical diversity as well. So I still get to look at enzymes, but just in fungal organisms.
It's so cool how fungal organisms are taking a page from the plant's book.
It's
um,
kind of the other way around, just because they've been around a whole lot longer.
wow, and this time I thought it was the other way. Well, with that, that wraps up the second vignette. We will now have 5 more minutes to take some more audience questions. David asks, I am from Colombia, and in my country, it is very common to use plants for daily use in baths for the body. They are widely used to cure or lower fevers without any distinction, but without organisms that monitor the doses of some preparations and make the population aware of improving use. What strategies do you know about addressing this problem?
Okay. As much as we can look at it as a problem, the thing is, I'm sure in Colombia, they have a system. They actually know how much is needed. It would be great if we could measure quantities, but most of these remedies did come from traditional healers or have been passed down from age to age. And so when you're using these herbal remedies, you tend to know how much to use. If one is not really knowledgeable in that, then yes, it is good to actually find someone. I come from a society as well where it's partially traditional healing or healing is very dominant. And so I think what I do know about that is people do know how to use it and why they're using it. And that is really just passed down from tradition to tradition. As we're going forward, and I mean, one thing we do know is that this is also moving back into the Western world, right? And so it would be nice, really. Most herbal remedies are not FDA approved and do not have to go through that cycle. So it would be nice to really start looking at having a system of QA for that. But right now, that is kind of far. But it might be feasible in the foreseeable future, just because people are using um, more plants or botanicals for healing or for daily uses and purposes. So I hope that answers part of your question. It's two-sided and there's really no answer to it.
We have two pretty related questions from the audience. The first is, in what ways have you used terpenes? And the next question is, how are terpenes different compared to other chemicals? Are they produced by plants in a higher amount compared to other type of molecules? Are they easier to produce by plants?
I think when you pick your plants to work on, it's not necessarily that when you're picking a system to work on, it's my boss worked on terpenes, so I like terpenes, and there are lots of other classes of chemicals that one can work on. There's a whole range, and it's not that they're highly produced. Just to note, most of these chemicals are actually produced in very minute amounts because, as we said, they're not really utilized for a lot of essential purposes for the plant. So it just depends what you're working on. Some are produced in high levels, some are produced in low levels. And just to really add on to that, that's actually one of the reasons why we study how they're produced. There is this translational or sustainability related issue, is that as we understand how they're produced by a plant, you do not have to go back to a plant to extract it. You can actually now produce it in a different organism. So that's just an addition to your question as well.
Um, here's another Here's another question from the audience, while we're still talking about terpenes. Someone in the audience says, I've heard that marijuana, the plant that has THC, has terpenes. Are these terpenes special, and are they responsible for any of the medicinal properties of the plant?
Okay, so that's a great question. And so marijuana does actually produce a range of terpenes, okay? And the levels of the terpenes, it's like a fingerprint for each cultivar. And so one of the So all of these different types of marijuana or types of cultivars or races would then have a different flavor of terpenes in them. And that actually contributes to their, to really their flavor and the effectivity. And so that's something that actually can be used to, you can use it to see the quality of your marijuana in years to come, if you could actually see that terpene profile. So I think all of these different cultivars will have different combinations of the terpenes. And most of the terpenes that are there in marijuana are also the same ones I tell you that you smell in the spring. Those are actually the same terpenes. They are nothing really special. They are just in different levels, and that's how they contribute to the flavor, as far as I know.
It's so amazing how different levels of terpenes can do very different things to us. I think that's about enough time for questions. Let's move on to the third and final vignette. So Dr. Mafu, we've talked a lot about plants, but I think the audience should get to know the person who's studying the plants. Can you give us more details about who you are and where your background is based? Particularly, how did you get interested in this topic?
Okay. Uh, so, so I'm going to start off with where I'm from. So I'm originally from Zimbabwe, and that's where I grew up and did my undergrad, and that after that I came here for my grad school. And yeah, and what's the second half of the question?
uh, no problem. How did you get interested in this topic?
Okay, so that comes into my, yes, okay, now I remember. So first time I could actually tell you that I've got an example of how I started this. 6th and 7th grade, they gave us a summer project, and it was, you're supposed to do something, but I then picked a traditional medicine, and because it's widely used, and started identifying the plants. That's the earliest I can remember of being interested in them, because I had my grandma who would religiously take some bark of something every morning in her tea, and it made her live a long life, and she was quite happy with it. And so that really was one of the earliest projects that I actually had. In my undergrad, I think that's where I learned to love enzymes. I did my project on looking at a biomarker. So we were looking at trying to figure out, there was a societal problem in that cats and dogs were being poisoned by people were feeding cats and dogs, or throwing it into the yard, so it would be thieves, this particular poison, so that they would then go in and steal. This is a very complex little thing. So we were looking for biomarkers in the blood of cats and dogs that would tell us whether they had been poisoned or not, so that they would know whether to give it some treatment, and it would be an easy way for vets to really be able to target that. I realized I did not like working with blood of cats and dogs, because I needed to, use that to be able to see how much poisoning they had been affected. And so I decided I like enzymes and I like metabolites, but I couldn't stand the cats and dogs. And so that's where my love for enzymes started. And that's where I was like, from now on, I'm working with plants. But I did like that I was given this ability, or this chance, to work on something that could be utilized by society. So when I went for my grad school, I always wanted to look for where I'd be doing the basic science, but somebody could use that as a tool for something else. And so I then would always look for opportunities like that. I went to South Dakota State. So from Zimbabwe, I then worked a couple of years, and then I went to South Dakota State. And there I worked on a plant which produced oils, and I was looking for enzymes that would produce these medium chain oils. And the reason for that was because these oils are produced by palm tree, And that is related to a sustainability because you have to import these and they're only produced in palm trees. And so looking for another way to do this would have been awesome. That failed, but it's still that's what I did for 2 years where I was looking for, I looked into this plant and seeing the potential or how it produced these. And this weed that I was working on is really grown in the prairies around Iowa. It's a weed, literally, and it grows in the Midwest quite predominantly and does produce these medium chain oils that we use for, the chemicals are actually used in toothpaste and in our daily things. Then I went on to grad school, and that's when I moved on to look at evolution of enzymes. And that's where I still am. And I'm hoping that it will translate into looking at some great pathways.
It's so inspiring to hear that your love for plant chemicals goes back way into your youth, and just fascinating to hear the path that took you to where you are today. Um, we talk a lot about the past, but how about a little bit into the future? What are the broader impacts of your research, for maybe in agriculture, for example?
The current projects that we do in our lab, although with a basic scientific, some of them are really just looking at plants and their metabolites and how we can look for new antifungals. There is a shortage of plants of chemicals or ranges of chemicals that can act as antifungals. And so we really just do inhibitory studies with those and seeing if we can make new antifungals. So that's more direct. So the work on the fungal organisms and where we look at how the biosynthetic pathways of those metabolites and those fungal organisms, it's really more and indirect. The more we understand what these particular metabolites do, it's looking for an indirect pathway to target that so that we can reduce the infectivity of agricultural crops. And so with hope, with time, we will find great antifungals or an indirect method to actually reduce fungal infection in agricultural crops. With all that I do, because it's very enzymatic and solving biosynthetic pathways, there's always a need for chemicals and a need for pesticides. And so as we figure out this enzymatic portfolios, it's really using, as we said, they're building blocks, right? And so putting them all together in different ways and trying to make new chemicals as well is something that I will definitely do in the future.
Definitely important work, and I'm excited to see where all of this work will go. That being said, I have another really, really important question. We talked a lot about plants, and you've studied a lot of them. But what is your favorite plant?
I can't really say I've got a favorite plant. I've got different plants which have got just different meanings in my life. And so the peace lilies are one of my favorite house plants because I was just excited the first time it flowered. It took me a long time to get it to flower when I was growing up. And so I've got very yes, I did that type of thing with it. And it is one flower that I do like seeing in the house. I also like flame lilies. And I think right now you might think that I'm very in tune with my youth, but with flame lilies, it's this plant that is really, actually, I think I have a picture, but it's a plant that it's actually the national flower of Zimbabwe as well. So I found out, but it was an emblem for my high school. And so we would always have it on our blazers. Greatest thing is that every year at the beginning of the semester, at the end of the semester, and we had a tri-semester system, would sing a song which was really based off our emblem. And so it's one thing I totally remember every day. I think I have probably sung that song greatly over 100 times. And yeah, and so recently I think about that because I've got a friend that I went to grad school with, and he figured out the pathway of one of the major compounds in that. And so I think it's just in my mind these days, because I'm like, oh, I should have done that because I sang that song for many years. So this is an example. This is a picture of the flame lily, and this is the emblem that we have. And that's the title of our song, Flame Lily, Burning Bright. It's also called Gloriosa Superba. And so it's really a beautiful plant. Okay.
I definitely agree. I can see why it's called the flame lily.
Yeah.
I might have a new favorite plant now. um, that being said, what are some things outside of your professional life that have influenced your work, or that influence your work, or vice versa? Has your work influenced your personal life?
Um, my work is, can't really say it's my work and personal life. I I have a child, and I really do a lot of things just for her. So it's really just my family is a very huge proponent for doing working well and trying to always do the best. I think I just want to be an example that you should always work very hard, try your best, and try and give back to society. And I would always want to be that role model for my child, and that's what really drives me. So I never want her to see me give up, or if I do give up, to know that you will wake up the next day and continue to do that. um, Education is very important to me. I feel people should have an opportunity to be educated, and that comes also early on. I feel that I at that time when I was growing up, um, women were marginalized in many different ways, whether it's access to education, uh, prioritization of a boy child, the fact that they could not get out of unfavorable domestic situations just because they were economically marginalized and did not have jobs. So I always felt that women need to be empowered, they need to be educated. And that drove quite a lot of my earlier reason to really go through school and really try and be good at what I do. So those things really drive me in a way. And right now, it's always, I feel it's getting better. It's not as bad as it used to be for women, but there's always still challenges. And I still believe that people, if we give people access to a good education and great opportunities, they can do a lot with their lives and really change a lot of things as well.
That is so heartwarming to hear and incredibly inspiring. And I'm certain that every day you are in that position as a great role model for your child and other people like her. That's a great transition into the final set of questions that we want to ask you. One thing we're all asking all of our speakers here at Science Cafe recently is how has the need for inclusivity and diversity changed how you do your work or present your science?
Okay. Um, so one thing I really love, it might not answer it directly, but you'll get what I'm saying. One thing I really love about being a professor is that you get a chance to, um, with time, I feel like you get a chance to really do the things that matter to you, whether it's going to be the science, whether it's going to be an adaptation for your science for the community. And um, currently, I feel like I've been given a lovely opportunity. I get to teach this class where I teach people how to make terpenes. And I teach you how to make terpenes, and focusing on the enzymes and the background of that. And it's an undergrad class, and people get this laboratory experience, which I feel is very important. And as I've said, I've been given a lot of opportunities to be able to be where I am. I feel that being able to give people those types of opportunities is also important. And that also then translates back to that I can also have undergrads in my lab. And the class I get to reach a wider range, but in terms of my undergrads that are in my lab, I really get to mentor, I get to really be there for them and teach them some science. I really hope they'll stay as well and make more chemicals with me or in that field as well. But really, um, at the end of it, it's really, I get an opportunity to give people the support that they would need to be successful and show them or highlight some of the opportunities that they would need to be able to follow their path. And that's really something that I get to do for now.
I completely agree. As a former student myself, these experiences and opportunities at a young age were instrumental in helping me find what I want to do. And that's incredibly inspiring that you're helping these students, have these opportunities. Um, I wish we had more time to talk about this because this is so lovely. But we only that wraps our third and final vignette. We'll be taking the rest of the time to take some audience questions. Catherine asks, is any of the common or are any of the common chemicals you mentioned before, are they used in a daily basis? Sorry, I'm misreading this. Are any of the common chemicals you mentioned before, um, are they very conserved in plants? Are they evolutionarily retained?
Um, and this would be in relation to the THCs, right?
I assume that and any chemicals that we mentioned in this talk.
Yes. And so, as I said, there are some chemicals that you do find in all plants in different levels. And a certain class or a certain family will tend to have them. Okay. And so the terpenes or these sesquiterpenes or these ones that are really more volatile, you tend to find them in a lot of plants because they are used really for the pollination, for communicating with the environment. It's just the levels or which one would be predominant. And so there is an evolutionary selection to them. And in some species, there would be a greater evolutionary like drive to keep them than others. But that's always going to be something you're going to have to look at that fingerprint for that particular group of plants that you're working on.
Eve asks, do other organisms, such as bacteria and animals, produce chemicals that are relevant to us, or are plants the superstars in the chemical world?
Sorry, can you say that again?
No problem. Do other organisms, such as bacteria and animals, produce chemicals that are highly relevant to us, or are plants the superstars in this chemical world?
Um, the animals are the least superstars. Okay, sorry to say this. We are definitely animals. It's not that we don't. It's just currently it's not the most. We have we're just not the best. Okay. So plants, bacteria, fungal organisms, okay, depending on which system you like, is definitely going to, are going to be the winners, right? And that diversity is different from organism to organism, but that it's in all types of other kingdoms. So the bacteria, the fungal organisms, and the plants, they all produce a beautiful range of chemicals. So you can't go wrong. You can pick any of them.
Bill asks, I have a very basic layperson's question. What do you determine, what do you do to determine what chemicals are in a plant?
Oh, I think I just did not talk about this. Okay. Okay, so that's a great question. So uh, I kept on talking about the enzymes and how you can build a pathway. Related to that, there is a whole lot of chemical analytical equipment that you can actually use to you would isolate your plant and grind it up really, and then you would extract it with some organic solvent, and so anything that would really extract the compounds that you're interested in, and you would just inject it or put it into this analytical machine, and there is a range of them, and they keep on coming up with a whole lot more of them, which is great because the sensitivity increases. And you'd get a profile. And so all you really see are peaks. I and yeah, all you really see are peaks in one way or another. My kid always tells me those are all lines. And then and then you take that information and you turn those lines into these structures that I had on all the slides. And so really there is a range of analytical equipment. When we look at the enzymes, we tend to I keep on going on to the sustainability and whether we can put it in something like baker's yeast, and so that you can make the pathway. So that's a different element where you can really reconstruct these pathways, put them into, vats with a baker's yeast to be able to make your compound. And so that's a different type of science as compared to really analyzing them with also the analytical equipment.
And it looks like we have time for one last question. Shu asked a very important one. What is the recipe of your grandma's tea, if you're comfortable with sharing it?
It after walking around to try and figure out which tree it was, I realized we actually had it across the road, and I'd spent the whole summer trying to look for it. But anyway, she just used to take some bark and she would boil some water, and that's what she would drink. She knew the levels. I didn't like it. It was very bitter. Never really hooked onto that, but it was really just boil some water, steep it in for a few minutes, and then just gulp it down.
I'd honestly love to try this tea one day.
I don't know about that. It's really anyway. If you like bitter stuff,
Oh, what kind of bark is the next question?
what kind of bark?
Yeah, what kind of bark did your grandma use to make her tea?
Sorry, I only know the vernacular name of that plant. So unfortunately, I still up to this day do not know the English name and whether it actually has an English name at all.
All right. It looks like we're out of questions, but that's great because we are also out of time. Dr. Mafu, on behalf of the Science Cafe team, I'd like to thank you so much for your time. It's been such a pleasure to talk to you tonight.
All right, thank you for the invitation, and this was really great. I got to talk about chemicals, so that's always fun.
And to our audience, thank you so much for joining us today. Our next event will follow the same format and will be held on the 10th of December. We'll be discussing nonverbal communication with Dr. Carrie Palmquist. You can check out our website at www.oebsciencecafe.org for more information. Goodbye and have a wonderful evening.